Okay, continuing on here, talking about the dot product, we have just established result 3 in the book, which tells us that the dot product of two vectors, we proved it in 3 dimensions, but it holds an arbitrary number of dimensions, that A dot B is always the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. What this allows us to do is to determine theta, the angle between any two vectors, because if we simply know, if we know the components of the vector, if we know the components of A and the components of B, then we can compute their dot product directly using our definition. We can also compute these magnitudes, and cosine of theta, of course, would be A dot B divided by magnitude of A times the magnitude of B. Of course, we can only do this if both A and B are non-zero vectors. If either of them is a zero vector, it doesn't make any sense to talk about the angle between the two vectors. And of course, theta is then just the inverse cosine of A dot B over magnitude of A, magnitude of B. Okay, so we can quickly just go back to the example from part 1 of the lecture in this section. Recall my first example of a dot product was V1 equal to 2, 2, negative 1, V2 equal to 5, negative 3, 2, and we computed the dot product of those two vectors to be 2. All we have to do to carry this process out is realize, okay, so the magnitude of V1 is the square root of 4 plus 4 plus 1. That's the square root of 9, which is 3. The magnitude of V2 is the square root of 25 plus 9 plus 4. Which is the square root of 38. So then A dot B is 2. So then we get 2 is equal to the magnitude of A, which is 3, magnitude of V1, which is 3, magnitude of V2, which is the square root of 38, and then times the cosine of the angle between them. So cosine of theta is 2 over 3 square root of 38, and theta is thus the inverse cosine of 2 over 3 square root of 38. I've already worked that out on my calculator earlier, which was in radians mode. You'll want to make sure, as usual in calculus, that any calculator work you do in trigonometry, your calculator should be in radians. This is approximately 1.46 radians. Okay, and what is it? Pi radians is 180 degrees. This is a little less than 90 degrees then. All right. So that's not a difficult computation. A lot of the computations in this class are not in and of themselves long or difficult. The challenge in this class is that a lot of material, a lot of ideas come at you, and it's just, it's the work is to keep track of everything, to have mental categories for everything. So you've got to really work at having an intuitive sense of what all these different definitions and formulas are saying. If you can have an intuitive sense of what's going on, the individual calculations, nothing like a related rates problem, is it? Nothing as challenging as a really difficult integral substitution or related rates or optimization. These computations here are short and sweet. That's not always going to be the case in this class, but often it is. And often the challenge for you is to be able to make sense of the forest and to just kind of understand where you are and what you need to do. Okay. I guess switch over to another page here. What the book calls result 7, and which is an immediate consequence of our new, result 3. Dot products. So just think of this. The dot product of two vectors is related to the angle between those two vectors. Suppose that angle is 90 degrees, or in other words, pi over 2. If the angle between two vectors is 90 degrees, or pi over 2, then those vectors are orthogonal. Those vectors point at right angles to each other. In that case, the cosine of that angle, cosine of 90 degrees, is 0. So it's an easy test to see whether or not the two vectors are orthogonal. Compute their dot product. If the dot product comes out to be 0, the only way that dot product could be 0 is for the angle between them to be 90 degrees. That's as long as we're not working with non-zero vectors. So two non-zero vectors, A and B, are orthogonal. In other words, the angle between them is 90 degrees if and only if their dot product is equal to 0. The only thing I'm going to say here by way of the proof is that this follows from 3. I guess one thing we could do is we could go back to the two vectors that we looked at early on, where my initial notes for those vectors are the two vectors v1 and v2, which had a dot product equal to 2. One thing we can now say immediately from this is that we know that v1 and v2 are not orthogonal vectors. They're not orthogonal because their dot product is not equal to 0. Whoops. So the two the two vectors that we've been working with in this section, which I've called V1 and V2, these vectors are not orthogonal, since their dot product is not equal to 0. All right. So another application of the dot product along the same lines relates to what are called the direction angles and direction cosines of a vector A. So let's again work in 3 dimensions here. A equal to A1, A2, and A3. And I will get this started with a graph. So let's sketch some vector A out here. And along with A, I'm going to sketch the standard basis vectors. So we've already seen what those are. The vectors I, J, and K. And I need to define what we mean by the direction angles of this vector. The vector A makes some angle with each of these standard basis vectors. So alpha will be defined as the angle between A and I. And if I can, I should perhaps do this with pencil. I don't think it's going to be weird. What I'm probably going to do is I'm just going to do it with, I'm just going to illustrate it once and let you kind of fill in the rest of the details. So, however this is going to, is that visible? Yeah, looks to be. Alpha is this acute angle that A makes with the standard basis vector I. And similarly, beta and gamma are the angles between A, I guess I could continue to, and J, and A, and K. All right, so these are the direction angles of any vector A. And what we want to do here is use dot products to express the components of the vector in terms of these direction angles. So consider A dot I. What is A dot I equal to? Well, we can get A dot I in a couple of ways. In one way, let's express A dot I as A dot B. So magnitude of A, magnitude of I, cosine of the angle between them, but we know that what we're calling the angle in this case is not theta, but alpha. So this is magnitude of A, magnitude of I, cosine of alpha. And let's do the same thing. Let's now simplify on each side. Come over here on the left and let's use the definition. What does our definition of dot product say that this is? Well, A, remember, is A1, A2, A3. If you take the dot product of A with 1, 0, 0, the only thing that survives all of those multiplications is A1. So this is A1. The right-hand side simplifies a little because we know that the absolute value of, I'm sorry, not absolute value, magnitude of the standard basis vector I is 1. So this is magnitude of A cosine of alpha. We can similarly compute A dot J is magnitude of A, magnitude of J, cosine of beta. This simplifies to A2 being the magnitude of A times the cosine of beta. And finally, A dot K is the magnitude of A, magnitude of K, cosine of the angle between those two vectors. And so A3 is equal to magnitude of A cosine gamma. We can now take all of this. See, now we have the components of the original vector A. We have A1, A2, and A3 expressed like this. So now we can say that A is equal to, instead of writing A1 here, I'll write magnitude of A cosine of alpha. Instead of A2, I'll write magnitude of A cosine of beta. And instead of A3, I'll write magnitude of A cosine of gamma. All right, so looking at this, we can factor out magnitude of A. Then we get cosine alpha, cosine beta, cosine gamma. But that's what A is, vector. Dividing both sides by the magnitude of A then gives us A over magnitude of A is cosine alpha, cosine beta, cosine gamma. And we've seen this before. It's a lot of new material, I get it, but we have seen this before. What is this? This is a unit vector in the direction of A. So, you know, that's that vector right there. A unit vector in the same direction of A. Now, occasionally, if it turned out that A were actually less than a unit vector, which is not the way I drew it here, then it could be the case that the unit vector is longer, but I'm standardly going to draw it so that it's shorter. That's the easiest way to see everything. But this vector here is then A over the magnitude of A, a unit vector in the direction of A. And notice what that gives us, or that's given by the vector which has, these are the cosine, the direction cosines. So the vector which has as its components the direction cosines of the initial vector, that is a unit vector in the direction of A. Okay, so I think I'm always getting to points. I was thinking about going ahead and starting another topic on what are called components and projections, but I think I'll break this up and do that in a separate lecture. So I'll start back up on components and projections in lecture 3.